Well, yes, we can definitely design and build the first lunar and Martian structures in order to establish our presence up there. We have the knowledge, we have the capability, and hopefully we will have the resources to do that. The Exostructures Research Group is one of the first civil engineering research groups that focuses on the design of these lunar and Martian structures from a structural engineering perspective. We are very lucky to have experts across many disciplines, for example, structural engineering, earthquake engineering, engineering seismology, geotechnical engineering, and so on. And we have people from different places. For example, from the UK, we're based at the University of Greenwich in London, and we have colleagues from Imperial College London, we have colleagues from the University of Dundee in Scotland, and we are very proud to have Foster and Partners as a very active industrial partner that help us conceptualize these structures. From Greece, we have also the National Observatory of Athens and Rcube private company that help us conducting this research. And here I would like also to thank the Engineering and Physical Science Research Council, EPSRC, for funding this research. Our vision is to develop a framework for the design of extraterrestrial structures that can be resilient against extreme natural hazards and that can be treated as critical in order not to allow damage for frequent loading scenarios. So how do I approach this? We think that the first lunar, for example, structure can be a long span storage facility that provides a shelter to valuable assets, for example, the different types of robots that we can have up there, energy fuel tanks, or even future habitable modules. This big structure needs to be resilient against extraterrestrial natural hazards, but at the same time, we would need to design and build this structure in a sustainable manner and to use as minimal structural material as possible, and of course, we need to use as little energy as possible during construction. The biggest issue up there first is the lack of atmosphere that leads to several different types of problems. For example, we might have very severe radiation levels at the surface. And that's why actually we need to build those big storage facilities in order to provide shelter from this radiation, as we said previously. The other fact is that we might have extreme temperature fluctuations at the surface as well, together with frequent meteorite showers. And yes, we are very concerned about the meteorite hitting our structures directly, but we have a larger probability of having meteorites hitting very close at the vicinity of the structure itself, generating seismic waves and therefore accelerating our structure like an earthquake, more or less. Or how we would call this a moonquake, for example, on the moon. And yes, we also have shallow moonquakes that can pose a threat to our structure itself. And we can have Marsquakes, for example, on Mars, together with sandstorms. So our first step in this project was first to identify strong ground motions related hazards, either from shallow moonquakes or from meteorite impacts. And we're very lucky to have Dr. Olga-Joan Ktenidou, an expert in engineering seismology from the National Observatory of Athens, that will tell you a few things and a few more details about these hazards.
Our team's task is to estimate the ground motions that will rock our future extraterrestrial structures. Everybody knows that InSight has been monitoring Marsquakes for the past 2 years since late 2019, but not so many people know that back in the 70s during the Apollo missions, full seismometers installed on the moon recorded lunar seismicity for almost 8 years. I'll tell you about how we tackle our task based on the lunar data, since they're much more plentiful at this time. And the truth is that there are many challenges that we're working to overcome. First of all, 8 years is a very short period of observation when we think of geological time. It only really allows us to record small, frequent events which may take place every year or every decade. But let's think to our design needs. Anything built on the moon is really quite precious. It's a critical infrastructure that we need to design to the highest standards. It should withstand even the very rare strong events which might only take place every few hundreds or even thousands of years on the moon, and we're missing those kinds of data in our recordings. To add to that, our moonquakes were recorded at very long distances, so what we actually see when we look at our data are quakes which have already attenuated enormously along the way. But to design resilient structures, we need to assume that they are situated pretty close to the quake. And let's not forget that seismic sensor technology in the 60s was really not what it is today. It could only capture a very narrow band of frequencies compared to the wide band of frequencies which our structures can actually feel. So again, we're missing part of the data. Our team works hard to overcome these challenges and make the best of the Apollo records. What we do is we perform theoretical simulations based on models which are calibrated on the data, but which can extend way beyond them into the scenarios which are critical to us. This is what allows us to predict how our lunar structures will shake under the design scenarios which they, as critical infrastructures, need to be able to withstand. And this is how we hope to help pave the way towards extraterrestrial seismic hazard assessment for the years to come.
Of course, our hands are tied when it comes to what structural material we should use for these structures. The obvious solution is to use what we have up there in abundance, and that is the soil, the lunar and Martian soil, called regolith. So we need to come up with ways to utilize regolith in order to produce structural materials that we can use for building structures. So there are this is a very broad and big open research topic at the moment, and some ideas is use additive manufacturing and 3D printing in order to create layered monolithic structures using this regolith, or we can even compact it and create some bricks in order to produce component-based or modular structure. But in this project, we decided to do a very small investigation and test some regolith-based materials ourselves. So what we did is we got this Martian regolith simulants, and we tried to compact it in order to create some bricks, and treated it thermally, and then in order to sinter it, and then tested it in compression and flexion. But we have the pleasure of having Dr. Panos Kloukinas at the University of Greenwich as an expert on this on adobe structures and on building with basically soil that will explain more details about this.
So, building settlements on Mars without being able to bring any material from Earth, not even water, and build with whatever is available there, just Martian soil. So this sounds like the Stone Age, if we exclude, of course, the rockets and the robots. So we have to take this reddish Martian soil and try to build something out of it. So we have to try and stabilize it and turn this loose material into something solid, into something like brick, like a clay brick, or a mixture of glass and clay. This one looks like. But if we bake it too much, it might end up like this. So this is what we're trying to do: optimize the stabilization techniques with whatever can be, with whatever conditions can be generated over there. Some mechanical pressure and some heating, which can come from the sun easily. And this is a very nice small scale first experiment we did, and now we have scaled up to a proper larger Lego brick or Jenga brick or whatever you prefer.
Now the other challenge is, aside the material itself, is now we need to create a resilient structure, but using as minimal material as possible. So what we did is we started from some conventional arch forms, for example, parabolic, semicircular, elliptical, and catenary, and via a developed form-finding algorithm, we created optimized varying thickness arches in order to sustain some static inertial loading. Then we further enhance these forms with the use of finite elements and XFEM in order to create some more resilient structures. We're very happy to have Dr. Christian Málaga-Chuquitaype from Imperial College London, our expert in structural engineering and optimization, and Dr. Nicos Kalapodis, our postdoctoral research associate at the University of Greenwich, telling you more about the methods we use to do that and what we have actually achieved or what we want to achieve in the future.
So, designing functional and safe off-Earth structures is a very challenging task. Space is indeed a very restrictive and aggressive environment. Take the case of the Moon, for example. Radiation is so severe in the surface of the Moon that you will not survive more than 7 hours if you are there without protection. You also have a very large variation of temperatures ranging from minus 180 degrees during the night to 100 degrees or over during the day. Not only that, resources are also incredibly limited. Construction materials are really expensive. It has been calculated that to put a single brick in the surface of the Moon will cost you something around $200,000 to $2 million. Therefore, we are constrained to what NASA calls in situ resource utilization, and is basically trying to build with whatever we find there. And therefore, this idea of 3D printing with regolith, which is the soil that is laying at the surface of the Moon or Mars, is quite appealing. Nevertheless, we also have to take the energy requirements into consideration, because most of these 3D printing processes will require some form of solar energy. And in the case of the Moon, for example, we have a 28 Earth day cycle, which basically means 14 days without energy. So whatever we design and build there has to be optimal, and optimal in the use of the minimum possible amount of energy as well as materials. And on top of that, whatever system or structural system that you design has to be almost 100% safe. It's not that you can call a 24/7 engineer to fix your cracks there, and any breach of safety will compromise severely the objective of the mission. And on top of that, you have all these hazards like meteorite impacts or seismicity, moonquakes, Marsquakes, which, combined with the low gravity conditions that we find there, can really pose a significant risk to the stability of your structure. So, what we are doing here at Imperial, in collaboration with the University of Greenwich, is trying to devise and advance new structural design and analysis methodologies tailored to these specific, very harsh conditions of extraterrestrial construction. We are revisiting centuries-old techniques like thrust line analysis that was used by the European master builders, but we are also exploring the use of more cutting-edge technologies like artificial intelligence and machine learning. Our objective is to gain fundamental understanding of the behavior of these structures in the low gravity and aggressive conditions that we find off Earth, and then to propose methodologies for the design of optimal structures while trying to safeguard the stability and integrity of our buildings all the time.
The offered structure will be arch-like ones and will act mainly in compression, so it is very crucial to secure their structural stability by considering phenomena like partial gravity or potential ground motions. Our team aspires to propose efficient structural forms that will guarantee both structural stability and material economy. First, we focused on thickness minimization of arches with regular geometry for various loading scenarios, including low gravity combined with seismic forces. To this end, our team developed an open source package named OpenArch. Subsequently, we developed and implemented numerical methodology that uses limit thrust line analysis to optimize the form of arches with regular geometry and constant thickness, which are abbreviated to CTAs. Specifically, this method uses the CTAs as inputs in order to generate optimized varying thickness arches that we call VTAs for reasons of brevity. Although limit thrust line analysis indicated that VTAs are the optimum arches because they ensure stability and up to 40% economy of structural material, finite element analysis highlighted that even these arches have some weak points. In particular, some excessively thin areas of VTA's geometry are responsible for the concentration of local stresses and the increasing of the possibility of a brittle failure. To fix this, we enhanced the VTAs by gradually increasing the thickness of their thin areas up to a point where the maximum tensile in-plane principal stresses exhibited cannot be reduced further. For a fair contrast, the enhanced VTAs were compared with their corresponding CTA counterparts. After tons of static finite element analysis involving enhanced VTAs, it became clear that for lunar gravity conditions combined with seismic loading, the enhanced VTAs that have been produced by parabolic inputs are the most efficient on the basis of the lowest tensile in-plane principal stress exhibited and material saving. At the moment, our team performs time history analysis with finite element involving only the most efficient enhanced VTAs and their counterparts so as to study their dynamic behavior in the lunar environment.
The next step, of course, is to validate physically what we tried to do numerically before. So we want to 3D print small scale these optimal arch shapes and spin them at the centrifuge at the University of Dundee in order to simulate low gravity conditions and at the same time shake them via these identified strong ground motions that we use from moonquakes, for example, in order to validate our numerical models and to actually see what we really achieved. Professor Jonathan Knappett from the University of Dundee is leading this as an expert in centrifuge testing and, of course, in geotechnical engineering. Therefore, our goal is to design resilient extraterrestrial structures or to develop a holistic framework for the design of off-Earth structures that can be resilient to extreme natural hazards from a structural engineering perspective. And for more information, you can visit our Exo Structures Research Group website. Thank you very much.